You're welcome again to Seremba Online School. My name is Mr. Katerega Fred. So we are going to continue from where we stopped in the previous lesson. Remember, we had studied the sound waves and we stopped with the factors affecting the speed of sound in air. Now, today we are going to look at reflection of sound waves. Reflection of sound waves. I saying it like light is reflected, also sound waves are reflected. Okay, so what are some of the laws of reflection of sound? Laws of reflection of sound. So in light you say that angle of incidence is equal to the angle of reflection. So here we are going to say that the angle of incidence of the wave is always equal to the angle of reflection of the wave. That is the first law. Angle, lower, we can say angle of incidence of the wave, the angle of incidence of the wave is always equal to the angle, is always equal to the angle of reflection, is always equal to the angle of reflection of the wave. Is always equal to the angle of reflection of the wave. And also another law, like you say in light, the incident whatever, the reflected whatever, and the normal. Also here we are going to say the incident wave. Now this is not a ray, is a wave. The incident wave, comma, reflected wave, and the normal, at the point of incidence, all lie in the same plane. All lie in the same plane. Now, reflection of sound, specifically, what does it drive us to? It is taking us to what we call the echo. Do you remember echo? The echo. What is an echo, class? What is an echo? You have ever heard about echoes? What is an echo? An echo is a reflected sound. An echo is a reflected what? Sound. But now listen briefly. This is what I want you to know about echoes. These echoes, for example, when you are in a big room, these echoes are always heard in bigger rooms, like in churches. You know, churches are big, mosques are big, and some other big halls, like some cinema halls. So, are you getting it? Echoes are mostly heard in big rooms, but in smaller rooms, echoes are not heard. Do you know why? They can bring a question. Explain why echoes are not heard in smaller rooms. In smaller what? Rooms. Are you getting it? Like in your room, you can be studying from a small classroom. So you will make it noisy and you will not hear any reflected sound. Do you know why? Because the original sound now which is produced, okay? The original sound, it quickly mixes with the other reflected one. Therefore, that one makes the echo to die out. You will not hear any echo. Are we together? They are not heard in small rooms because the original sound quickly mixes up with the reflected what? Sound. Okay? The reason is the reflected sound waves, the reflected what? Because the room is very small. Once sound meets the hard surface, as it is getting reflected, it is reflected so fast. The reflected sound waves return. The reflected sound waves return very what? Very quickly. Return very quickly and mix up with the original sound. And mix up with the original sound. And mix up with the original what? Sound waves. The moment they mix up, no echo is heard. That is the reason. Because you would expect sound meets the surface and then is reflected so that you can hear it. But during the process when it is being reflected, again it is mixing up. Therefore the echo dies out. You will not hear any echo being formed. But now, if you want to prevent echoes in some rooms, okay? That's why like you can use some softy boards on the walls, some softy bodies, some softy materials, because softy materials, they absorb what? Sound. That means that sound which would have been reflected will all be absorbed and no echo will be heard. But if the surfaces are hard, when the original sound meets the surfaces, it is reflected, because hard surfaces reflect sound. They don't absorb it, but soft surfaces, they absorb sound. Are we there? Now, let us go to the application of echoes. Where do we apply echoes? Applications of echoes. Application of what? Echoes. Then one, echoes are used in measurement of the speed of sound in air. We are going to talk about how we measure the speed of sound in air using the echo method. Are you getting that? We shall also talk about other methods, but we can also use this method. Measurement of the speed of sound in air. Are you getting it? That is an application. And another application, also echoes are applied in echo sounding systems. In echo sounding what? Systems. I'm going to give you an example here. In echo sounding systems, like these echo sounders are used like in ships. The ships, you know them? These ships which sail on water. They have that echo sounding what? System. And it has a transmitter and the receiver. Are you getting me? Now this is sound which is produced in that area where the ship is. Okay? That system works in such a way that the sound is transmitted up to the bottom of the sea. Are you getting me? Then when the sound is reflected from the bottom, the receiver receives it. So that system is set in such a way it can help whoever is sailing that ship to determine the depth of the sea. For example, can know that now where we are heading, the water is very deep, and here the water is very what? Shallow. Therefore, echoes are applied in echo sounding system to measure the depth of the sea. To measure the depth of the what? Of the sea. That is a practical application. Are we there? Let's go on. Then also, they can be used to measure distance. Okay? Measurement of distance. So you can use echoes because when sound reaches and it is reflected, okay, the speed of sound in air in that case will be twice the distance, because sound travels to and from. It meets the surface and then it comes back. That is a to and fro movement of sound. That's why speed is equal to distance over time. I'm using this formula twice d, because it goes and comes back over the time taken. From here you can use that formula, then you can be able to get the distance, measurement of distance, and so on. So other applications, they are there in our notes. Then we are going to talk about an experiment to determine the speed of sound in air using echo method. That's why I've told you in the applications that echoes are applied in the measurement of the speed of sound in the air. So, let me give you an experiment to determine the speed of sound in what? In the air. So, this is what we need. An experiment to determine, this is very simple, to determine the speed of sound in the air by echo method. I'm specific. We are using echo method. I've told you there are other methods we can use to determine the speed of sound in the air. But now we are using echo method. This is what I need. Okay? Like now you are home, you are having your sister or your brother. Now if you and your brother or you and your sister, you are going to be my experimenters. Are we together? I'm going to get two experimenters. One is going to be experimenter A, another is going to be experimenter what? B. So, one experimenter claps his or her hands. Now when you are at home, you can even do this experiment. It's a matter of getting your brother or your sister and you start. Are we together? So we need two experimenters. The ones who are going to be executing this experiment. Two experimenters, A and B. Two experimenters, maybe A and B, stand. Are you seeing it? Now you're going to stand at a certain distance from a vertical wall. Are you getting it? For example, you are standing at a certain distance from the wall of your house at home with your brother. You are the experimenters. You are here, your brother is there. You are here, your sister is there. So you are going to execute this experiment. Now you are the experimenters. One is A and another one is what? B. Stand at a known distance. Stand at a known distance. This distance, you need to know it. Let us say stand at a known distance D from a vertical wall. Like I'm standing here. You can see I'm facing a certain wall. From a vertical wall. Now that's the distance. When you stand, what is the role of one experimenter and what's the role of another experiment? So, experimenter A claps his hands. Okay? Or she claps her hands. One claps her hands and the other one starts the stop clock simultaneously. The reason as to why one experimenter A claps his hands and B starts the stop clock immediately. Okay? So when I'm clapping, for you are recording the time taken. You remember during the process of clapping, because we are standing at a distance from a large vertical wall, we expect a various number of echoes to be heard. Therefore, the time taken for any number of echoes to be heard is noted. That's why one experimenter is having a stopwatch clock. Are we there? Then the time taken, remember the original sound, it is coinciding. So with the reflector, so the time taken for any echoes is what is noted, because you are clapping the hands and now you're hearing the reflected sound. So you must note the time taken for any echoes is noted. That time, let us say the time taken may be T. The time taken T for any echoes is noted. Then, if there are very many echoes, any echoes, and you have noted the time, also you need to know the time taken for one echo. So the time taken for 1 echo, time taken for 1 echo is equal to the time taken for 1 echo, that is the capital T. I seeing it? The periodic time. And that time will be equal to the overall time over the number of echoes. I seeing it? That one will be the periodic time. Time taken for 1 echo is obtained from this. It will be the overall time over the number of what? Echoes. Then therefore, the velocity or the speed, the velocity of sound or the speed in air is calculated, okay? Is calculated from, remember velocity is equal to distance over time, okay? Velocity in this case will be distance over time, okay? So what is the distance in this case? The distance, remember sound goes and comes back. So it's calculated from this expression. This distance we are talking about, we are standing up from the vertical wall, sound goes and comes back. Over the time. The time. Now the time here is equal to the capital what? Capital T. I think the capital T, which is the time taken for 1 echo. Because you, after noting the time taken for all the echoes, we need the time taken for 1 echo, which is the capital T. Somebody can transform this from this. If you put here T over N, then therefore V finally can become 2D to make the reciprocal N over T. Where D, that distance, N the number of echoes, then this T is the time taken for any echoes. So this is the formula for the velocity. It can be got from that expression. If you want to go further, you can express it like that. You come to the conclusion. So briefly, that is the description of the experiment. I beg to stop here. We shall continue from there. In our next lesson, we see some calculations about echoes. Okay? Thank you for watching.